Hello everyone, and welcome back to NL 582, Modeling and Control of Electric Machines and Drives. In the last lecture we start talking about the field connections of DC machines. So as we discussed, it's just the DC machine has two members, as much of the old machines we'll be talking about. To have a stator, which is the stationary part, and the rotor, which is the rotating part. And we said that the rotor of this machine is the armature of the machine because it's the place where the electric part of the energy conversion happens. And the stator, or the stationary part of this machine, is what we call the field member because it holds the field winding, which produces you the magnetic field you want. And why we need a magnetic field, as we said at the very first lecture, and keep saying that all the time, the magnetic field is our medium for energy conversion in electric machines. So if you have a motor and you input an electric energy to be converted into mechanical energy on the shaft, you need to have a magnetic field for this energy conversion process to happen. Because if you remember, the torque production requires that you have a coil carrying electric current and cutting a magnetic field. So you need a magnetic field here. Okay. The electric current moving inside the coil is the electric energy you are just pushing to be converted, but it will not be converted unless you have a magnetic field, which is your medium of conversion. The same idea with the generator. To get a generation of electric voltage, you need to push a mechanical energy to rotate a coil cutting a magnetic field. So the mechanical energy you're pushing, the torque you're pushing from an external mean, is your input mechanical energy that will be converted into electric energy, but it will not happen unless you have a magnetic field present here. Again, because the magnetic field is your medium of conversion. But a very, very important hint to have in your mind all the time is the magnetic field is just the medium. It's not a part of the energy conversion process. Why this important? We'll be talking about this in a bit. Okay. So, in large DC machines, which is the typical DC machines, the field coming from electromagnets. That means it's coils with applied voltage to it. So electric current moving inside a coil will create a magnetic field, just like the permanent magnets. So that means you have another set of winding will be in the stator to produce a magnetic field. Okay. Beside the primary set of winding, which is the rotor, which is the armature winding, where your energy conversion happens. So the other set of winding on the stator, which is just all its job is producing the magnetic field you need as a medium for energy conversion. Okay, so it's another set of winding required also to be supplied by electric voltage to pass electric current into it to create the required magnetic field. Okay, so this can be having three forms of connection. The first one is the separately excited. That means you need a separate DC source for the field winding to supply it with the required current. Okay guys, so this is the connection you can see here. For a motor or for a generator, is just you have two separate circuits. The right hand side one, just like here, so this one here is the armature circuit, and this one here is the field circuit for a generator, and the same idea, that is the armature circuit, and this one is the field circuit. Okay, so you have two separate circuits because you have two separate sources. Okay, that's why it's called separately excited machine. And we just went through all the equations and we talked about this. The second connection is the shunt excited DC machine. From its name, shunt means parallel connected. It's just you don't need here a separate source, but you just connect the two sets of winding, the field winding on the stator and the armature winding on the rotor. You just connect them together in parallel. Okay, so if it is a motor like this, you just use a single source and it will be connected to both of them, supplying current to both of them. That's IF moving here and that's the armature current moving here. Sorry. Okay, and if it's a generator, the generated voltage out of the machine like this will be just supplying both, going to the load, that is the terminal current, and it will also some of it go into the field winding to create the magnetic field. So the whole point is just connected the two winding in parallel or shunt connected at those 2 points. Okay, and we talked about this, And in order to control the amount of current moving through this field winding here, and that is the amount of field you'll be creating. From this connection, you need to have a series adjustable resistance connected in series with the field winding, like this. Okay, so by controlling this adjustable resistance, you will be adjusting the amount of field current moving here, and this by definition just control the amount of flux, magnetic field, that you will be producing inside the machine. To control the flux, the same mean by separately excited connection, it's much easier because you have a separate source for this, so you don't need to do anything but controlling this source. By controlling this source, you're controlling also the amount of current. Of course, you can do the same idea by adding also a series resistance to the field winding in the separately excited machine. So it's up to you, and it's up to your engineering solution to use a controlled DC source for the field winding, or also to use adjustable resistance in series with the winding, just like the shunt connected machines. Okay, guys? And we introduced the idea of the torque speed characteristics for motors. It is just for any motor you need to know, and for each kind of machine we'll be dealing with this, you need to know what is the relationship you can find between the speed and the torque of the machine, because that's very important. That will tell you how the machine will be just acting to the change of the mechanical load. So I've been talking here about motor mode exclusively. Okay, so the whole point here, it is just like this. What will happen if the load torque increases? So if the load torque increases, the motor torque, the developed torque out of the motor, need to increase to accommodate this increase in the load. Okay, and from this equation, if you see here, if this torque of the motor goes up, from this equation, if you just work it out, you will find that the speed will go down. So if you just plot the relationship, the torque speed characteristics for the separately excited or the shunt excited motors, so it will look like this. Yeah, it's a linear relationship that's starting high and goes low like this. That means with the increase in the torque, the speed drops. And that makes sense. It acts like a brake. If you increase the load on the motor shaft, that acts like a brake, and the motor speed will go down. So the torque developed by motor will go up to accommodate this increase in the load torque, but this will come at the cost that the speed will go down. Okay, guys? That because from seen here like this, so the variables in this equation and this torque speed characteristics is the speed, of course, and the torque, but you have the flux also as a second variable because you can't control it like we said before. Okay, here the terminal voltage, we don't play it most of the time, and here the armature resistance. So the terminal voltage and the armature resistance, most of the time we don't play with them, so they're constants like here. So the other variable here is the flux. If you play with the flux, you'll also play with this torque speed characteristics. So like we said last time, is from this equation, if you just increase the flux, the speed will drop down at the same value of the torque. That means the whole torque speed characteristics will be just shifted down like this if the flux goes up, and it's vice versa. If the flux goes down, the whole one will be shifted up. So if the flux goes down, you will have another torque speed characteristic that's up like this. Okay, it will go up if you reduced the flux. Okay, and that means the speed will increase at the same amount of torque. So that means you will not playing with the torque here, not playing with the load. So it is the same load you can supply and all stuff, but you can supply it as different speeds just by controlling the flux. And that's the very first idea we've been just contacting, the idea of the drives or the control of the speed of machines. So I can still accommodate the amount of torque that my load requires, but at another speed that just coming out from the natural characteristics of the machine like this. You can just control the flux, and this will control you the speed. Okay, guys? Also this from the same equation like this, we just have another notice. It is just the flux here is in the denominator of the equation. That means if you have a zero flux, you'll have an infinite amount of speed. So we said that's a very, very important hint for separately excited or shunt machine, that it has never to be started at zero flux. So you have to make sure that the machine has enough magnetic flux before you apply a terminal voltage for it as a motor. Otherwise, the speed will jump to a very high speed, and this will bring you a mechanical failure. The shaft can be break down, you can have accidents, and we don't like this. So that's a very, very important safety precaution to have in mind here. Okay, guys? Another precaution we'll be having here, or another hint actually, we'll be talking about here for still separately excited and shunt machine before jumping to the next connection, is for shunt and separately excited winding. Okay, so the winding, or just say the field winding, okay, has high number of turns per coil, so you need high number of turns, okay, with thinner cross-sectional area for the wires. Okay, why are we making this? That's why I told you it's a very important hint to have in mind. Thus, the magnetic field is just the medium for energy conversion. It's not a part of the energy conversion itself. So it's something, it has to be there for the energy conversion to happen, but we don't want this to be very much. Okay, sorry, it's not a part of the energy conversion itself. So if you go back to the equivalent circuit, and let me talk about this. So you have here our field. That is our field, okay? And here is the terminal voltage. And if am I talking about a motor, for example, that the terminal current, that is the armature current, and that is the field current. Okay, guys? So that is the total current coming from the supply going into the machine if it is a motor, okay? And it's the same principle actually with the generator, but it's just for example here. So the amount of energy that will be really converted inside the machine is represented by the armature current, because that is the one going inside the machine. That is the E armature. Okay, guys? So the amount of energy going into the armature circuit here, so the energy going to this circuit, is really the converted energy. Okay, so the energy that's really going into the field winding here is not a part of the energy conversion. Okay, we are not calling it as losses. It's not something we lose actually, because we need to create a magnetic field for the energy conversion process to happen, but it's not a part of the energy conversion. So if you apply a certain amount of energy from the load, that is the total energy coming from here, from source supply, sorry, okay, you need as much as of this input energy, as much as you can to go here into the armature, and as less as you can to go inside the field circuit. Okay, but without sacrificing the amount of magnetic field we need to create. Okay, guys? So how we do this? Simple as this, because for shunt excited or separately excited, it will be the same idea. Okay, so if you can create the same amount of field you want by as less current as you can, that will be much better. Okay, and if you go back to electromagnetic fields equations, the flux simply equals N times I divided by the reluctance. Okay, N is the number of turns, and I is basically the current, and the reluctance is the reluctance of magnetic path. It is the equivalent of the resistance in the electric circuits. So if you see from here, to create a certain amount of magnetic flux, it is basically the multiplication of number of turns by the amount of current divided by reluctance, of course. So you can create the same amount of flux by reducing the current if you increase the number of turns, and that's what we're doing here. That's why I'm saying for the field winding here, we need to have high number of turns to get the same amount of magnetic flux we need with a smaller amount or a smaller value of current going through the winding. Okay, guys? And if this current will be small, like we said here, That means we just need thinner cross-sectional area, because the cross-sectional area of the wires, of the copper wires you used for any coil, is just determined by the amount of current moving in. If the current is small, you need just a small cross-sectional area. If it is large, you need larger cross-sectional area. Okay? And by definition here, guys, if you have a coil with small cross-sectional area and high number of turns, high number of turns means just you mean high length of wire. That means you need a long wire to be just wrapped for a high number of turns. Okay, by definition that will give you high coil resistance. The electric resistance will be high. That means R field will be high. This resistance R field will be high. Okay, guys? And that just all makes sense. If this resistance is high enough, that means the current going it will be very small, because it's Ohm's law. Okay, for the same amount of voltage applied to it. Okay, if this resistance is high enough, the current will be very small. Okay, because just I field will equals from here V field divided by R field. V field here is the same as the terminal voltage because they are all connected in parallel. Okay, so if R field is high, that means I field will be small. Okay, guys? So by using high number of turns with thinner wires, we basically creating the same amount of field we need, but with smaller amount of current. And why we need this? Because we need to minimize I field as much as we can to let IA to get the highest portion of the total current here, because they are parallel connected like this. So basically the terminal current will be just the addition of I field. So I terminal, which is the total current, equals IA plus IF, because they are just basically shunt excited or shunt connected here. Yeah, so we need to minimize I field as we can to keep IA as much as we can, because IA represented the converted energy, while IF is just the one that's need to create the magnetic field, which is your medium here. Okay, guys? I hope you get this. Okay. So now we talked about the separately excited machines and the shunt excited machines. Okay, the third connection here, and you have a third connection which is series connected field winding. Okay, guys? And from its name, it's just very obvious that we connect field winding in series with armature winding. Okay, so the equivalent circuit will look like something like this. Okay, that is R series, which is the field series winding, and RA, that is the armature resistance, and that is the induced EMF. Okay, so for a motor mode, you will need just one DC source like this. This will be your V terminal, this will be I terminal, which is the same as I field and the same as I armature, because they are all connected in series. Yeah, so IF will equal IA equal I terminal, because they are all connected in series like this. Okay, guys? If we're talking about a generator, it will be the same idea. That is RS, RA, but now the source is basically the induced EMF, because that's a generator now. Okay, and you have a load, electric load connected here, so that is our load. That is for generator mode. Okay, and it will be IA equaling I field equaling I terminal or I load. They are all the same like this. Okay, guys? So the same idea. Rather than having a separate source for the field winding, you just connect it in series with the armature winding and just apply one single source, and it will just produce enough current for both of the winding. Okay? Also, the generator is the same idea. Okay, guys? Using the same thing, how we can just control the field here if you want to control it. Okay? So to control the field, to control I field here, because that's a series connected, use adjustable resistor in parallel with field winding. Okay, so you bring this RS here and connect an adjustable resistor in parallel with it. Okay, so by controlling this adjustable resistance value, you will be controlling the amount of current moving through here. So the current that will be coming from here, the terminal current like this, it will be divided between the two resistors because they are in parallel. So that is I field, and call this I adjustable. So by controlling this adjustable resistance, you will be just controlling this ratio until you get the exact amount of I field you want. That is the current moving inside the series field winding. Okay, guys? The same principle will be talked before with shunt excited, with simple modifications to accommodate the difference between shunt or parallel connection and series connection. Okay, guys? So, doing the same idea, we can now just derive our equations. Okay? So, the armature equation, the armature voltage equation, will be from the circuit you're seeing here, from our generator. Okay, so V terminal will equal EA plus or minus current, and I will call it I armature. Do the same, I armature or whatever it is. Okay, multiplied by RA plus RS. Okay, guys? Yes, if you have adjustable resistance, you know this RS here in the equation will be just replaced by the equivalent of RS and R adjustable together in parallel. You know the idea, okay? If there is no adjustable resistance, it will be just RS. And did the same idea back in the shunt field winding also. R, which is we have in here, and the equations for the shunt equation. Let me just call it back for you. Yeah. So here, yeah, that is the equation, sorry. So that is V terminal equals EA plus IA RA and all that stuff. So that is the armature equation. Okay. For the field equation, if you remember, that is VF equals IF RF. Maybe I can call it back. I think it will be found here. Yeah. VF equals IF RF here. So this RF will be just RF if you don't have adjustable resistance. If you have adjustable resistance in series with this, it will be RF plus R adjustable. You know this, okay? So that means it is the total field resistance. If you have adjustable resistance attached to that in series or in parallel, that means when you use it in the equations, you just use the equivalent resistors for those. Okay, guys? Sounds good. So, and you know the idea. It is plus for motor mode, like this. V terminal will be higher than EA, which is induced voltage, and it is negative for generator mode, because like that EA will be higher than the terminal voltage, and that is the way things are working. Okay, guys? The same like we said before in shunt excited and separately excited, that the flux is just directly proportional to the field current. Okay, guys? But the field current here equals the armature current. so that means it's directly related to the armature current. Okay, and for small amount of currents, or for small currents, that means in the steady state, which we're more concerned with all the time, phi will be basically equals a constant multiplied by this current. Okay, it's directly related to it. Okay guys, it is just, if you want to plot the flux with I armature, will be linear like this. Okay, so C here is just a constant, keep it in mind. So just get this and let's substitute in the equation we had here. So V terminal, I'm sorry, so V terminal will equal EA, the armature, the induced voltage of the armature, which equals K phi omega M. Should be memorized this for now. Okay, and this for motor mode, yeah, and let me just concentrate on motor mode for now. It is just for example, you can derive the same idea for generator mode easily. So this plus will be a negative for generator, like we said before. So you multiply IA by RA plus RS. Okay guys, so we take phi here and just replace it by CIA, like we said. So it is KCIA omega M plus IA multiplied by RA plus RS. Okay, so V terminal here will be equaling KC omega M plus RA plus RS, all of those multiplied by IA. Okay, so that is the equation representing this current for the motor mode. Okay guys, for the generator mode you'll just have, so the plus is for generator mode, this plus for motor mode. If it is a generator mode, it will be just negative like this. Okay, that's simple. Okay guys, fine. And if you want to calculate the torque using the same idea, if you remember, the torque equals K phi times IA. That is the principal equation we'll be using all the time. So in the same idea, we substitute for the flux here to be C times IA, that is the flux, and this multiplied again by IA in the main equation. So this gives you that the torque here, that the motor torque, or the load torque, keep that in mind, equals KCIA squared. And that's a very, very important relationship. K is a constant, C are constant, so multiplied together they're basically a constant. So from this equation you get that the torque of the motor here for series connection directly connected by the square of the current, of the armature current. Okay, and what did that mean? That means that series connected motor, okay, produces a very high amount of torque. That makes it, this kind of a motor, is very convenient for traction applications. So traction application means cars, trains, elevators, all that stuff, because those kind of loads, they need very high amount of torque. So the series connected motor is very, very preferred for these kind of applications because it's produced a very high amount of torque. It is the square of, or just proportional to the square of the current. Okay, so that is a very good kind of motors if you want a very high torque. Okay, but while it's so good like that in terms of producing very high amount of torque, it will have a problem we'll be just investigating now, while we just look at the torque speed characteristics. Remember, as I said, for any kind of motors we'll be dealing with, we'll be looking at the torque speed characteristic of the machine, so that's very important here. Okay, guys? So, doing the same idea, if you just go to these two equations, Vt and torque, okay, and you just find from I here in terms of the torque and just substitute it in the equation here for Ia, you will be getting the torque speed characteristics. So in terms of math here, so you just saying this from the torque equation, Ia squared, let me write in black, sorry. So Ia squared will be equal the torque divided by Kc. That means Ia is square root of the torque divided by Kc. Okay? And you just substitute this in the other equation, which is the V terminal, will be equaling, sorry, getting it back, Ea, or the last form of it, Kc omega m plus Ra plus Rs, and this plus because just we're dealing with motor mode here, multiplied by Ia. You just take this Ia from here and substitute it here and just do the simple math. You'll just get the relationship between the speed and torque. It will look like this. Omega m will equal V terminal divided by the square root of K multiplied by C multiplied by 1 over the square root of the motor torque. That's minus Ra plus Rs divided by Kc. That is the torque speed characteristics of the series connected motor. Okay, guys? That is the speed and that is the torque under the square root here. Okay? So it's up to you whatever you want to control here to control the machine. Okay, guys? So if you try to plot this equation, just use generic numbers and plot it. That is the motor torque here, and that is the speed of the machine. These characteristics will look like this. Okay, guys? And that is the whole point we are just dealing with here in these kind of machines. And the same idea, if you just increase the torque, that means increasing the load, the speed will start dropping like this. Okay, guys? Like any other kind, so like the shunt motor and all that stuff, but it's not the same like the characteristics for the shunt or separately excited motor. The difference here is like you see here. For zero torque at the start of this, the speed is very, very high, almost infinity. And that's why that's a very, very important stuff to keep in mind when you're dealing with a series motor. That a series motor must not be started at no load. Why? Because no load means the load torque equals 0. That's the definition of no load. And that means the motor torque will be 0 because the motor torque is just trying to accommodate the amount of load torque. So it will be almost 0 because if you remember when you talked in the tutorial that the motor torque will need to accommodate the load torque and friction and inertia torque. But the friction and inertia torque is just very small fractions compared to the load torque. So that means if the load torque is 0, that means the motor torque is almost 0. And the load torque, if it is almost 0, like this, from this equation and this thing, that means omega m will be equal infinity. So you will have just a very, very high speed, again, that will damage the motor and even cause accidents. And we don't like this. So keep that in mind. We cannot start a series motor at no load. you have to connect the motor to a load before you start it. You cannot just leave it like that and give it electricity and let it start, because it will just go to a very, very high speed and it may be damaged and cause accidents. Okay, guys? Okay. So that's a very important hint to have in mind also here in series motor, like we had before in the shunt motor when you said you cannot start it at 0 flux. Here you cannot start it at 0 torque. Okay, guys? The torque here means the load torque, of course. Okay? And it is the same idea we talked about before, is just how you just accommodate here the field winding. So that is RS, and that is RA, and that is the induced EMF of the machine. That is EA, and that is the V terminal here, guys. The same idea, it is just the converted amount of current, is the current going into the armature circuit, okay? And from you seen here, it is the same current moving through the series winding, okay? So we don't have the same problem we had before when we have shunt connected, because we need to minimize the amount of current going to the shunt winding as much as we can to leave the rest to go to the armature winding. Yeah, here they're connected in series, so you already have the same amount of current moving through both of them. Okay, so it is the contrary here, because IF, or the I field, equals I armature, and I armature is by definition is high because that's represented the amount of energy converted. Okay, so you already has high amount of flux of current moving through the series winding. So as IF equals IA, which is high enough, so we need few number of turns for series field winding, because remember we said that the amount of flux we need to create by this field winding is just the multiplication of the number of turns by the current divided by the reluctance. So because we have high current here, we will need small number of turns, sorry. Okay, so for series connected field, we just need few number of turns, okay, but with large cross-sectional wire areas. Why? Because the current is just high, and we said if you have high current, you need high cross-sectional area to accommodate this amount of current. Okay, guys? So that will mean that RS is small, not like RF when it was just shunt connected. It was very high, and that's with just very good, because if it is very high, the current moving through it, which is IF, will be small, and that's what we needed, and the shunt connected or the separately excited. But here in series connected, on the opposite side, we need RS to be as small as possible because it is just connected in series to the armature. Okay, so to keep I armature high, we need both of those resistances RS and RA to be as small as possible, because they're just connected in series. Okay, guys? And that's how we do this. That's basically because this IF equals IA and it's high enough, we don't need as much number of turns as we needed before to produce the same amount of field we need. Okay, so we just use small number of turns. That means the wire will be just small. Okay, the length of this wire will be small, while large cross-sectional area to accommodate this current will reflect in just smaller resistance for RS. Okay, guys? So it is just a way of thinking of how we design these winding. Okay, and that's the engineering principle of all of that. We don't just deal with equations and all stuff, but we need to just also think all the time of the engineering concept behind this, how to design stuff, how large we need it, how small we need it, and it's all connected together with these physical concepts. And that's the beauty of electric machines. It is just you combine the physical aspects the math we do with all the equation derivation, all that stuff, but you have to put your engineering concepts all of the time. Okay, so you will have all the time a wide broad options you can choose from, but here's come the engineering principles, what to choose and how to design it. Okay guys, so those are the three different connections: the separately excited, the shunt excited, and the series excited motor. Okay, and they will be having different equations to just differentiate, and they will have just different stuff. Okay, so if I need to just conclude these connections, so there's the equivalent circuits of all of them, and I'll be doing this for motor mode just as example. That is the V terminal, and that is the I terminal, and that is IA. That is, this I terminal will be also I armature by definition, and that is RF, and that is VF. Okay, that is another one, and that is IF, and that is separately excited. Okay guys, for shunt excited it will look like this. You will have here RA, and in parallel with it you will have RF, and this will be your induced armature voltage, and here is V terminal plus minus V terminal. Okay, that will be armature current, and that will be field current. Let me do this in black just for best visual. Okay, and this is shunt excited. Okay, and for series excited we will be having this in series RS and RA, and that is EA, and that's plus minus terminal voltage, and here will be just I terminal or I armature or I field. They're all the same. That is series excited. Okay guys, so those are the three different connections you will have for the field and armature winding for this kind of machine. Okay guys, the last thing I want to just discuss with you here is what we call the power flow inside the machines. Okay guys, so this machine can be working as a motor, and if it is a motor you will have the power moving like this. Okay, that we call it the power chart. Yeah, so here is your input. What is the input of the motor? It is P electrical. Yeah, you have electric power input, so you have electric power input going to the armature of the machine. That is electricity coming outside. Yeah, when entering this you will lose some of this power as P over the resistance of the armature. This is copper losses on the armature resistance RA. You know this from electric circuits. Yeah, whenever a current, electric current moving in a resistor, you will lose some of the power over this resistor. That is copper losses. Yeah, and at the same time you will lose also some copper losses over the field resistance. Okay, that is copper losses on RF, the field resistor, or RS, that is the series connection. So you know it is the same idea of whatever connection you have, because also you have current moving in the field winding, and whenever you have current moving in anything that have a resistance, you will lose some power as we call it copper losses. That being transferred to be a thermal energy. You will just notice that any kind of electric appliance, if you just touch it, it will look hot. Okay, the thermal energy comes from this power losses because it's transferred into thermal energy. It's inevitable, because we're not dealing with something ideal here, guys. Wherever these wires have resistance, it will have copper losses in it. Okay, so you push electric energy through the armature of the machine and also through the field winding. Both of them need electricity. We're talking about a motor, yeah? So these energy go, and you lose some of it as copper losses on both of the winding, on the armature winding and on the field winding, okay? And the rest will be converted, and that is the converted energy you need to be converted, because that's an energy converter. So the electric energy, you need it to go and be converted into mechanical energy, but not all of it will be converted, because you will lose some of it before it's converted. And these losses just go in here in the copper losses over the armature winding and over the field winding. And the rest of it will be converted, and that's the amount of energy we're more concerned with, because that is a converted energy, yeah? So this converted energy and the mechanical energy that's converted on the shaft, no, actually you will also lose some of it, as we call PFW. F means friction, and W means windage, okay? So the friction, that means you lose some of the mechanical energy by friction with the mechanical parts of the machine, okay? Because that's mechanical parts are just have friction together while rotating, yeah? Because this machine is just, you have the shaft connected to a mechanical load, and they have this kind of bearing to hold it, so they are all have friction together, so you lose some of the mechanical energy on this friction, okay? And while the windage, that means the friction also, but with the air while rotating. So your rotor and your shaft, all the rotating parts of the machine, will have a friction with the air while it's rotating. It's touching the air all the time. And this air has some kind of a resistance to the rotation of the machine, so you lose some of the energy to overcome this resistance of the air and keep rotating, okay? So you lose some losses here, PFW. Sometimes we call it the mechanical losses. It's obvious. It's some sort of mechanical approach for this power loss. Some of it with the friction with the mechanical parts itself, and some of it what we call windage is the friction with the air while rotating, okay? And the rest is the output mechanical power you needed from the first part. So for a motor, you input electric energy and you want it to be converted into mechanical energy, but live is not that easy because it's not an ideal system. You will be losing electric losses here on the copper winding, on the copper losses, sorry, in the winding, and you will lose some mechanical energy for the friction and windage. Okay, guys? So those guys here together, we call it the P loss, the power losses. And that's obvious. You input P electrical and output P mechanical, but you lose some of it on the way. Okay? A good designed machine will have as less power losses as possible, and that's your job as a designer for this kind of machine, to have as much gain or efficiency that we call here as possible. Okay? So the efficiency of any kind of machine, we call it eta. Efficiency of the machine will be equaling P output over P input. For here, it's P mechanical over P electrical, and multiply by 100 if you want it as percentage. So you want this efficiency to be as high as possible, and to do this, you need these power losses to be as low as possible. Okay, guys? So that was the thing for the motor mode, okay? The generator mode should be very obvious now. It is just the opposite way around, because the generator mode, you will have mechanical energy input. So the input here is P mechanical, and everything is now reversed. The mechanical energy, you just lose some of it as friction and windage, and then the least of it, of the remaining part, would be the converted energy. And from this converted energy, you will lose some of it as copper winding, because this mechanical energy now is converted into electrical energy. So this converted energy is electrical now. Okay? So you lose some of it on the copper winding on the armature, and some of it on the copper winding of the field. Okay? And the rest output will be the electrical energy here. So I did the same idea, but it's just the opposite way. Now your input is mechanical energy and your output is electrical energy, and the losses, it is the same types of losses we just encountered before. Okay, guys? So how to calculate all those kinds? Easy. So if you want to calculate the copper losses of the armature winding, PRA will equal basically IA squared times RA. And the copper losses on the field winding will be I field squared times R field. And it's different from a connection to a connection, which current and how to calculate these currents, IF and IA, but whenever you calculate them, you just plug it in here and you just find these copper losses. Okay, guys? And how to calculate the friction and windage losses? We cannot calculate it by math, so this is experimentally estimated. So you can just estimate it in the lab. I'll be talking about this in the coming machines when in the lab, how to estimate the friction and windage losses. But for a problem to solve, a mathematical problem, it will be either given or not. So if it's given, the friction and windage losses, then you use it. If it's not given, that means assumed to be 0. And this amount actually will not that much. So the friction and windage loss is not usually a very high number. But you cannot have a mathematical equation for it. It's all empirical formulas coming from experimental estimations. Okay, guys? So these are the power losses, the 3 types of power losses we have in DC machines: the copper losses on the rotor, on the armature, and the copper losses on the field winding, and the friction and windage losses. Okay? For the converted power, it owes all the time the torque of the motor multiplied by the speed. Okay, guys? And if you just substitute for the torque here to be K phi IA, that is the equation you know, and omega m will be EA divided by K phi. You know this. EA equals K phi omega m, so omega m is AA divided by K phi. Now K phi goes with K phi, and this will equal EA times IA. Remember, guys? So it has 2 different forms. One is the torque times the speed, and one is the induced voltage times the current. Why? Because the converted energy has 2 types here. For the motor mode, this converted energy here is basically mechanical, because it is in the motor you convert electrical energy to mechanical energy, so the converted energy will be mechanical. But for a generator, the converted energy here will be electrical, because the generator converts mechanical to electrical energy, so the converted amount will be electrical. You know this. So the converted energy can be calculated from the mechanical side by multiplying the torque by the speed, or from the electrical side by multiplying the induced voltage by the armature current. Okay, guys? That sounds good. And by the way, this omega m, like we said before, is the angular speed in radian per seconds, but it can be calculated like 2 pi over 60 times n rpm. And the n rpm is the speed in revolution per minute, and it's more convenient to express the speed of any rotating machine by the number of revolutions it rotates in a single minute. So most of the time you will know this value. So to convert it to omega m, which you need in all the equations we derived, you just multiply by 2 pi over 60. Okay, guys? So this is how to calculate the converted power. Okay, guys? And from just having this chart in your mind, you can just play around a lot. So for example, if you have a generator and you know the mechanical input power and you know the friction and windage, so you can easily calculate the P converted by saying it equals P mechanical minus P friction windage. Simple as that. And if you know P converted and you want to calculate the output electrical power, you just say P electrical equals P converted minus PRA minus PRF. And that's why we call it just a chart. Okay, guys? And we'll be just having examples over this in the next tutorial. Okay, guys? So those are the power flow for this kind of machine, for a motor and for a generator. I hope those principles we've been talking about in DC machine will be a very, very good and solid background when we just jump into the more important ones, the synchronous machines and then the induction machines we'll be dealing with in the next lectures. Okay? I hope this was informative and exciting. Take time to study this, and I will be very happy to get your questions on Friday's morning's meetings. Thanks so much for joining me today, and I will be seeing you